Okay guys, in this video we're going to be talking about the electron configuration of many electron atoms. And so we're going to explore how electrons fill up the different atomic orbitals for various atoms. And this is what's called the electron configuration. So let me show you here. The electron configuration refers to the arrangement of electrons among the available subshells within an atom. And so we're going to be learning the so-called electron configuration notation. Here's an example for the lowest energy electronic state of a carbon atom. So recall that neutral carbon has 6 electrons, and this notation suggests that 2 electrons are occupying a 1s orbital, 2 electrons are occupying a 2s orbital, and the remaining 2 electrons are occupying a 2p orbital. Okay, so this is the type of thing that we call an electron configuration. Another way of representing the electrons within an atom is by using what's called an orbital diagram. The orbital diagram shows additional information not contained within the electron configuration. It shows the spins of the different electrons. So here in this orbital diagram for carbon, we see that the 2 electrons in the 1s orbital have their spins paired, in the sense that 1 electron is spin up and 1 electron is spin down. And in order to satisfy the Pauli exclusion principle, which we talked about in a previous video, the 2 electrons would need to be paired so that neither electron has the same set of quantum numbers. Likewise, we have an electron pair spin up and down in the 2s atomic orbital. And then here we see that the 2 electrons that are in the 2p orbitals, you have 1 electron that's spin up in one of the 2p orbitals and another electron that's spin up in a different 2p orbital. Recall from the previous video that the 2p subshell involves 3 unique atomic orbitals with different spatial orientations. Those 3 dumbbell shapes that we looked at previously. On the next slide here, what I'm showing are the energies of the different subshells for a mini electron atom. We notice that the 1s atomic orbital has the lowest energy. Then we have the 2s orbital. Then we have the 3 2p orbitals. Then the 3s orbital. At higher energy, we have the 3 3p orbitals. Then the 4s orbital. Then come into play the 3d orbitals. Then the 4p, then the 5s, 4d, 5p, 6s, etc., as you go up the table to higher and higher energies. Different electron configurations are obtained by populating these different atomic orbitals. And there's different ways that you can do that corresponding to different electronic states. A given atomic orbital can have no electrons in it. It could have 1 electron in it that could be either spin up or spin down. Or it could have an electron pair where 1 electron is up and the other electron in that orbital is down. What we need ultimately is to be consistent with the Pauli exclusion principle, such that no 2 electrons within the atom can have the same set of quantum numbers. We're always bound by that. And in this problem, what we are being asked to do is to consider these electronic configurations and determine whether they are possible. That is, are they allowed electronic configurations, or do they somehow violate the Pauli exclusion principle? So let's go through these. In part A, the electron configuration that we're given is 1s3, 2s1, and so the question is this an allowed electronic configuration? And if you recall from the previous slide or our previous discussions in the past videos, a 1s orbital can only hold at most 2 electrons. And this electron configuration is suggesting that there are 3 electrons in that orbital. Okay, so this is not allowed. You can't have 3 electrons in a 1s orbital. The next configuration we have 1s2, so that's okay. 2s1, that's okay. An s orbital can have one electron in it. And then we have this 2p7, okay? And so there's something wrong with the 2p7. If you look at the diagram here, we see that there are 3 unique orbitals, and each of them can hold, at most, 2 electrons, which means you could have a maximum of 6 electrons within the 2p subshell. This electron configuration is suggesting that there are 7 electrons, which is 1 too many, so that's not allowed. Okay, so this is not a valid electron configuration. Here we have a longer electron configuration. That's okay. We'll just go through it piece by piece. 1s2, there's nothing wrong with that. 2s2, that's acceptable. 2p6 is acceptable, right? Maximum number of 6 electrons allowed in the 2p subshell. 3s2, that's okay. 3p6, also acceptable. 3d8, let's check that one. 3d8. So here we have the 3d subshell. There are 5 unique orbitals. Each of them can hold 2 electrons for a maximum of 10 electrons in that subshell. So if you have only 8 electrons in there, you're still good. Okay, so 3d8 is acceptable. And then finally 4s2, 2 electrons in a 4s orbital. Right? You have a single 4s orbital. It can hold at most 2 electrons. So this is a valid electron configuration. There's nothing wrong with this electron configuration. Let's look at part D. Here we have a 1s2, that's okay, 2s2, and then a 2p4. Okay, it's not more than 6, so there's nothing wrong with this configuration. Oh wait, yeah, part D. Yes, so this configuration is acceptable. For a moment there I looked at part E, 1s2, 2s4. We know that that's not going to be good, right? You can't have 4 electrons in a 2s orbital because there's only one unique spatial orbital that can hold at most 2 electrons. Okay, so that's not acceptable. For F, we have 1s2, 2p6. Oh, I skipped the 2s. 1s2, 2s2, 2p6. These are all fine. 3s2, followed by a 3p10. Okay, that's not going to fly. You can only have, at most, 6 electrons in a 3p orbital, or a 3p subshell, and so that's way too many. The 3d10 was okay, but the 3p10 is not. Okay, so this is not a valid electron configuration. It would violate the Pauli exclusion principle. Each of these that I've crossed off, they would all violate the Pauli exclusion principle. You would have multiple electrons with the same set of quantum numbers, and that's not allowed in quantum mechanics. Okay, so let's talk about the difference between a ground electronic state and an excited electronic state. So atoms can have many possible electron configurations. One of these electronic configurations is going to have the lowest energy, and so we call that the ground state electronic configuration. All other electronic configurations correspond to excited states. And so here's an example for sodium. The ground electronic state of sodium has this electronic configuration. Right? We see the 1s orbital is filled, the 2s orbital is filled, as is the 2p, and then there's 1 electron in the 3s. Okay, so that's all of the electrons in sodium, and this is the ground state electron configuration. What you could imagine doing is taking this 3s electron, this 1 electron in the 3s orbital, and promoting it to the 3p. Let's go back to the energy level diagram and show you what I mean. So if we have that last electron in the ground state of sodium is in the 3s orbital, if you move it to the 3p, the atom is going to take on a higher energy. Okay? And so I've used a star here to denote the excited state, or to denote that this is an excited state. And so this is a perfectly valid electron configuration. It's just not the ground state. That's all. We make a distinction between so-called core electrons and valence electrons. Core electrons correspond to these inner shells of electrons that are typically filled in an electron configuration. So the core electrons of sodium are the one s electrons, the two s electrons, and the two p electrons. The valence electrons are the electrons that are in the outermost shell of the atom. And these electrons are important because they are the ones that are responsible for determining the chemical properties of atoms. Okay? Oftentimes, we will not even bother writing the core electrons, and we will use this core notation here, where the in brackets neon means that the core electrons of a sodium atom have the same electronic configuration as the ground state of a neon atom. And so we'll only focus on the valence electrons for the sodium atom. So these are two equivalent ways of writing the electron configuration for the sodium atom. In this case, we show all of the electrons explicitly. In this case, we focus only on the valence electrons, and the core electrons are so-called isoelectronic with the neon atom. Here is a list in periodic table format of the valence electron configurations for all of the atoms in the periodic table. And what I wanted to highlight is that these electronic configurations are determined through a combination of experiments and also computational calculations. So sophisticated quantum mechanical calculations that are compared with experiments to determine what these electronic configurations are. So ultimately, they are experimentally determined. So the ground state configuration of a hydrogen atom is 1s1. For a helium atom, which has 2 electrons, it's 1s2. 2s1 for lithium. This is the valence electrons. Note that the core electrons within lithium are equivalent or isoelectronic with the helium atom. And we are going to go through these probably in the next video. So what we're going to do very quickly when we begin the next video is to go through these different atoms and learn how to predict what the ground state electronic configuration of the atoms are. So there's some rules that we can use that usually work to determine the ground state electronic configuration. So I'm going to go ahead and stop this video here. We're going to pick up with the Aufbau principle in the next one.